Maybe I'll start now. So welcome to the second talk on algebraic number theory. So let's maybe start by recalling what we talked about last time. So I'll be working with a number field F, which is a finite extension field. The degree here is n. So the most important concept we introduced last time is the analog of the integers for a general number field. It's called ring of integers, OF. So it consists of elements in the bigger field in the big number field F, such that alpha is a zero of a monic polynomial with coefficients in Z. So that's somehow a better way to define what the ring of integers is in general context. And it's independent of the choice of the generator of F over Q. And let's also recall that what kind of important thing why we want to study number theory, because we kind of need, it's kind of just, by the example we talked about Fermat's last theorem, we need some sort of factorizations like understanding somehow the factorization, or why? Remember the first step we tried to kind of approach the Fermat's last theorem was to factor things like this. And then, of course, later on we want to factor Z and X and Y later on. But this is the factorization exists in this ring of integers Z adjoint zeta P, where P is a prime, odd prime. So that brings us to today's topic, which is to understand the factorization in the ring of integer OF. Okay. So let's recall that over Z, we have a really good, one of the most important theorem about Z is that every integer, maybe every positive integer, to avoid the negative, positive integer is the product of prime numbers in a unique way. Up to permutation. I'll try to write bigger. Okay? So this is the unique factorization in Z. Everybody knows that. But the problem is this property might fail for OF. Okay? But instead of sort of talking about a case, talking about the case it fails, let's talk about the case when it doesn't fail. Let's give an example where you still have a unique factorization and see what that means. I'm going to consider Z adjoint I, the imaginary number I. This is going to be a unique factorization domain. The reason is, I think you learned this from abstract algebra. That's because Zi is an Euclidean domain. Oh, sorry. Let's spell excuse me. Sorry. And this implies it's a PID, principal ideal domain, and therefore it's a unique factorization domain. But let's see. Let's make it more explicit of what the factorization like in Z adjoint I. I think this is somehow the first example of the ring of integers of a number field, and I think we should understand it by all means. But here's a fact. Every element let me call it x in Zi, is the product of prime element. I'll list the prime element later on up to permutation and up to multiplication by a unit. In my case, it's just plus minus 1 plus minus I. Let me give you an example, a really quick example. So if 2, I mean the most obvious way you can think of it is like this. Right. 1 minus I, 1 plus I. But you can also write it as minus I minus 1. You can put minus I on both sides, I guess. So they're considered essentially the same thing. And by some sort of, in some sense, you can also write it as 1 plus I squared times negative I. Let's think about it. So 1 plus I squared is 1, I squared is negative 1. So 1 cancels with negative 1. So this is 2I. So 2I times minus I is 2. So maybe this is a better way in some sense. You write 2 as a prime square times a unit. This is somehow maybe a more intrinsic definition. So now I'm going to list all the primes. All prime elements in Zi. There are, well, 1 plus I is one of them. But whenever I list a prime element, I implicitly say, okay, 1 plus I, this is also a, associated to that, this is also another prime element, and also 1 plus I times I, and also minus I times 1 plus I. Okay, so but later I'm gonna only write the first one, 1 plus I, but not the other 3. Okay, because they're all like off by our units. But I want to point out the norm of all these numbers, which is 2. So by definition, recall that norm is just 1 plus I, 1 minus I in this case. So it's 2. Okay? So what are other primes? If P is a prime number, whenever I say prime number, I really mean an actual prime number in the integers of type 4k plus 3. So this is actually a prime element in this bigger domain, Zi. Again, whenever I write P, I mean minus P, IP, and minus IP there. And the norm of this number P, because they're both embedded, is just P, the number P itself, so it's P squared. Thirdly, so I'm going to have some, so for P, a prime of type prime number, or people call it rational prime, same thing. I can have something called U plus IV, where U and V are given so that their sum of their squares is P. So it's a theorem Gauss that every prime of type 4k plus 1 is the sum of 2 squares. So U plus IB is going to be a prime in Zi, and also U minus IB is going to be a prime in the adjoint I. And of course, this one the first one you can also multiply by plus minus 1 plus minus I, the second one also. So there are essentially, if you want to find a prime whose norm is P, there are 8 of them. Where like this one will produce 4, the other one will produce 4. But there are essentially 2 classes, U plus IB and U minus IB, up to multiplication by this unit. And this theorem will say that X will be equal to some U, which belongs to plus minus 1 plus minus I, times 1 plus I to some alpha, say, times P1 beta 1 PR beta R. So these are 4K plus 3 type primes. I'm just writing out in a straightforward way. And then I'll have times, okay, U plus IB1 RS BS. So let's give it some power gamma 1 gamma S. And then I can have some U1 minus IB1, say delta 1 Q S minus IB. Okay. So that's a complete factorization of an element inside Zi. This is up to a unit. Instead, well, like you could choose here. You can choose not to use 1 plus I as a representative of this class. You can choose another representative to put here. You can still get a similar factorization, except the U will be changed a little bit up to whatever you change here. You just make the changes on the first factor, basically. Okay, so that's what the unique factorization means in this ring of Gaussian integers. Are there any questions? Yes.
Do we know if there are fields for which the ring of integers is the Gaussian integers?
Oh, so the field is just Q adjoint I, right? The fraction field of this. So, yes, that's a good question. I should have said this. So this is my F, and OF is the adjoint I.
And more generally, if we start with a ring like this, do we know whether we can find a field that has this as its ring of integers? Is that
I think theoretically it's better to go from number field back down.
I agree.
Yeah.
Okay. Say that.
I think logic goes that way. You have to make sense of what you mean by a ring like this. If Z adjoins some algebraic numbers, you just basically do the same thing, adjoining that to Q. But then, of course, this ring may not be the ring of integer for that number field. So if it's not a ring of integer of that field, it may not enjoy the property I'm going to talk about later on.
So I guess my question then is, what's the most general result we have for pick a ring and show that you can find a field who has that ring as its ring of integers?
Take a fraction.
Okay.
Yes, that's fine. Oh no, ring of integers. Somehow, if you think about the ring of integers, it has some sort of a relative. If you think about it really, it has some sort of relative feature.
Yeah.
Right. You have this F has to be over some Q, and you have some sort of base Z. Mm-hmm. Sometimes this. I mean, if you look at the definition of OF, it requires to have coefficient Z. So what it amounts to say is that I guess there's some concept in computer algebra that the ring is integrally closed. So that could be a kind of a generalization of this in general rings. Sorry. We can talk about that later more. Okay? So now I'm going to come to a non-UFD example. It took me a long time to decide which field I want to take this example. I'm going to take a very complicated one. I hope you don't mind too much. You can take an example of -5. Go with this complicated one. Okay? So my OF, note that negative very nice come to 1 mod 4. I deliberately want to take this one so that the ring of integer is a little bit complicated. But still fine. So I want to give a factorization. So just 5 is 10. But I want to say this is the same as this. Let me write out one more step. So this is, what, 4, 1 minus 19, gives me 39. So this is 40, and then this is 10. Okay? So we have factorization like this. As it turns out that 2 and 5, and all these things, and these two, are irreducible elements. Namely, this cannot be factored further into two elements which are not units. Maybe I can prove one for you. Or maybe okay. Maybe I'll leave the exercise for you to prove. But I want to point out that this is not sort of very straightforward in the sense that we have these 4 elements, which they're all irreducible elements. Somehow we have this 10 factor into irreducibles in 2 different ways. Okay? So that means this is not going to be a unique factorization domain. Because, I mean, like you have 2 different ways of factoring things. I want to say that a similar statement. For example, you can do 2 times 5 equals to, there's obvious thing. You can factor it like this in Zi. Does not contradict. That Zi is a UFD. Because what you can do is you can further factor this. Because really, I mean, like 2 times 5 can be factored as, let's move the numbers in a good way. So 1 plus I, 1 minus I, that's 2. 1 plus 2I, 1 minus 2I. So that's 5. And the other 2, you can kind of trust me, because obviously I did this exercise before I come. Okay? So somehow these two, like in Zi, I guess this number 2 and 5 are not irreducible. They can be further factored. The reason you got 2 times 5 equals to 3 plus I times 3 minus I is because each one of them has some sort of common factor. And you can further factor, they would just be the same after swapping the factors. So this is no contradiction to Zi being a UFD. Whereas over here, this 2 and 5, they cannot be further factored as in the adjoint I. So that's somehow one reason. But now, let's think about this again. How do we fix the problem? I mean, let's maybe go back to think about the Fermat's theorem. We really want a factorization to work in order to prove it, because we really want to take advantage of this, things that are being co-prime and then to further factor. But what do we do? To fix this in this OF. So here's the idea. So let me go back to Z. Let's talk a little bit about ideal theory. The word ideal, of course, you learn it in the ring theory. It's sort of some subsets closed under multiplication by the elements in the ring. But then, I think the first time it shows up is to solve this question. How do we solve this issue? I think somehow, as Keith explained to me, it was first introduced to somehow sort of say some sort of ideal stuff that somehow will represent the GCD of 2 and this factor, and 2 and the other factor, and so on. Somehow later on, I guess they have a more concrete way to write it down. So that's what you've learned in the ring theory. So let's go back to Z and see what happens. So you have what's the idea of generated by two integers, m and n? Well, just think about this. What's the idea of generated by 4 and 6? In 4 and 6, of course, there's a 2 there. If you have 4 and 6 in the ideal is closed under addition. So that's definitely 2 there. So once you have 2, you don't need 4 and 6 because there are just multiple of 2. So it's just the same as 2. And if you think a little bit more, you realize that the ideal generated by m and n is just a GCD of m and n. Generated by GCD of m and n. So really, in some sense, you should really think that taking xy is sort of the same as taking GCD of x and y. At least this is what's happening in the number field. That's somehow the intuition I want you to have. So also I want to recall the ideal multiplication, which is maybe multiplication of ideals. So say my I is the ideal generated by a bunch of numbers, and j will be the ideal generated by another set of numbers. Find the numbers, but it could be infinite. It works in the name. Then I can multiply two ideals together. This will be the ideal generated by the pairwise product of the generators of the two ideals. So pairwise product. Of generators. Okay? So let's see. Let's back to our example. Maybe I'll just come back a little bit more here. Let's see. Let's cover this. I don't need this anymore. So let's think about this situation a little bit. So let's go back to the case when it's not a contradiction. So what happens is that this 2 and 5 each further factors into, I guess, a common factor of 2 with, if you can think it's kind of like common factor, common divisor with 2 and 3 plus I, and common divisor 3 with 3 minus I, or something like this. And we're going to somehow have that idea here. I want to say, over here, this is because 2, instead of writing the element, I'm going to write the ideal generated by 2, is the reason that we have this equality is because there's some factor 2 and each of the factors on the right-hand side has. And 2 is a product of those two factors. And the 5 is sort of the same thing. And same for the other, on the other side. I'm not sure if I want to complete writing all of this. It's 5. This is already here. If these equalities were true, then of course this product, this equals the other one, seems to be obvious. In the sense that, it factored into 4 different factors, it just, it groups them differently. So maybe, for today, let's just sort of check one. So maybe I'll just check this one as an exercise. But let's just do it here. And the rest you can do as an exercise to actually work out the numerics. Okay? So you understand that, right? I mean, like if each of the factor has this, then this equality is just basically regrouping these 4 factors in different ways. So let's check this equality here. So what do I have? I have 5 So I need to take pairwise product of these generators. I have 25 here. I have 5 times 5 is 25. 5 times this factor is 5 minus 5. Yeah, this is the part I don't like about this example, which is it's a bit tricky to write all this. And then the last one is this. Okay, you have a priori 4 generators. Later down, of course, I want to show this is really generated by 5. So I have to compute each of the factors. Care about it. Start with the last one. So this is what? This is actually 1 minus negative 30. Over 4, this is just 10. So last one is 10. Again, in an ideal, you know, once you have 25 in the ideal, you have 10 in the ideal, then you have their difference, and you have their difference of the difference, whatever. So once you have 25, then you definitely have 5 in there. For example, it's like 25 minus 10 times 5. It's definitely in the ideal. And you can put everything else in here, if you want. But now you realize once you have 5, you don't need anything else. Because 25 is the power of, it's a multiple of 5. This is also a multiple of 5. This is also a multiple of 5. This is 10. It's also a multiple of 5. So therefore, it's just 5. So in the ideal, once you have 5, you don't need, like in this ideal, once you have 5, you don't need anything else. So therefore, we verify this equality here. That, you know, the ideal generated by 5 is really the product of these 2 factors. And by the same argument, you can verify the other 3 equalities. So I hope to use this example as a way to convey that using factorization. So maybe I should write it. So upshot. Here's upshot. I want to factor into ideals instead of elements. So instead of really factoring a number into a product of prime elements, you want to factor things into prime ideals. So this is precisely what Dedekind proved. So I said this OF is a, of course Dedekind didn't say it's a Dedekind domain. We later call it Dedekind domain. What it means is that it's an integral domain in which every ideal, every non-zero proper ideal I. So what these two means is that basically you don't want I equals 0 or I equals everything. So you want to exclude these 2 cases. Can be factored, well, uniquely. But later on, whenever I say uniquely, I really mean unique up to permutation of the factors as the product of prime ideals. And also, I want to say that if you know what it means, every prime ideal, every non-zero prime ideal is a maximal ideal. Okay? So in the example here, what I have, in this example, what I have is the factorization of 5, the ideal 5, into, it turned out these 2 are prime ideals. So this is one of the factorizations you see. So again, I want to emphasize the upshot is that you want to factor things into ideals instead of elements. So for number fields, for some purpose, working like ideals are better to work with than talking about elements. Okay? Are there questions? Comments? Okay. So now let's talk more about the factorization. I want to bring back to this relatively general setup of my Z and bring the integer OF on top of that. Okay? So inside of here, Z, I have a prime number. Whenever I write P is a prime number. So one of the important things I want to understand is that how does this P factor the ideal generated by P? What kind of avatar of the element P in the bigger ring? You can also write it as P times elements in OF. This is how you define the ideal generated by P. By the unique factorization properties in the Dedekind domain, or like the Dedekind theorem, this factors as a product of a bunch of prime ideals. Okay? So you have these factorizations. So I'm going to introduce a theorem now to give you how to compute this factorization in practice. So the earlier example we did, maybe just put it here, is that I want to factor 5 inside, this is factoring 5 inside this ring of integers for Q adjoint root of negative 39. So this is a factorization. This is somehow the same factorization in Z adjoint, 1 plus root of negative 39 over 2. So how do we get this in practice? So assume that, say my number field is generated by one element. For most of the case, I'm going to take my alpha to start to this is also algebraic integer. Just for example, in my case, I can take root of negative 39 actually. And there's a technical condition that I want P to not divide the difference between
the index.
Excuse me. Difference is fine.
Nobody calls it the difference.
I call it difference. That contradicts your statement.
Nobody I've ever known before.
Okay, the index of V the adjoint alpha inside OF. Why do I make this assumption? Well, this is because somehow, although OF is more canonically defined, but in practice it's really easier to work with Z adjoint alpha. So I want to, for practice it's easier to work with Z adjoint alpha in some sense. So there's this condition here. So suppose that, let's see. So let Hx with coefficient Z is the minimum polynomial of alpha, and H bar x is just Hx mod P. So let's live inside Fpx. This is a reduction of Hx mod P. And suppose that now I have a polynomial with coefficient in the finite field, Fp. Hx itself is reducible as a polynomial over Z, but the reduction may be further reducible. So suppose this is equal to H1x with some factors. Hg x e to the g. It's a factorization.
Got an overline in the HG.
Pardon me?
The overline in the HG.
Oh, thank you. Okay. Yes.
Is this a different H bar from the one we just defined, or is it the same?
It's defined H bar to be Hx mod P, and this will further factor as given. And you can see that I already kind of hinted that these numbers are going to be the same. Okay? Then, this P, namely POF, will be factored as an ideal which looks like this. Alpha to the E1 P, comma, H, G, alpha, E, G. I mean, I wrote here without, I have it here without saying that, these HIs are different. Otherwise, you just group them together. So then this would factor as this, where HIX is any lift of HIX bar. So what the last line means is that you have this polynomial where coefficients lives in FP. But of course you want to write something in integers to represent that. So this HI will be some way of representing that. So that's a factorization. Let me give an example. Quickly come down to an example. So let's see. So let's just take this one. Take this complicated imaginary quadratic field. This is really complicated. So I want to take alpha to be not the generator of the ring of interest. Because for a lot of time later on, as we talked about last time, this OF may not be generated by one element anyways. So I just pick some alpha in OF. Then as we talked about last time, that the difference of the actual ring of interest, the index of the adjoint root of negative 39 in the actual ring of integer is 2. You're missing the 1 plus root of negative 39 over 2. But I want to say, for example, I want to take p equals 5. So we're fine here. As long as my prime does not divide the index here, we're fine to use this theorem. Now I'm going to use this theorem to calculate the factor of 5 inside OF. So how do I do that? Well, in this case, the minimum polynomial of root of negative 39 is obvious, x squared plus 39. Right? So now I want to mod 5. So when I mod 5, this is, what's the best way? Minus 1. And it does factor as x plus 1, x minus 1. In F5. This is brilliant design. Can't write properly. So okay, so the reduction of hx by mod 5 factors x plus 1 and x minus 1. So now my theorem tells me that this ideal generated by 5 would factor as 5 with alpha. Well, actually, let me just write it, alpha plus 1 and 5 alpha minus 1. So that's what the theorem says. So however your minimum polynomial mod p factors, you sort of have to factor the prime in the same way with this sort of recipe here. Of course, in my case, it's just I'm just rewriting what I have. Okay, so that's how you get the factorization. And good. So that's how you do it. Like basically, you pick the minimum polynomial of the generator, and then mod prime p, and you factor that polynomial, and you're done. And then for those who are very careful, and you can say, wait a minute, this is different from what we had earlier. They look a little bit different. So what's going on? Right? I mean, this looks a little bit, well, close enough. But looks a little bit different. Right? So I want to say that they are actually really the same factorization, except they look a little different. So let's see, what is obvious? So this ideal here is definitely inside the first factor here. Okay? Because I mean here you have 1 plus root of negative 39 over 2. And here this is twice of that. Of course, this lives in here. This is so the first ideal is contained in the second ideal. But in fact, they're equal. In fact, if you take the element in the second, the generator of the second ideal, one of the generators of the second ideal, which doesn't look obvious coming from the first one. You can write it as remember 1 plus root of negative 39 over 2 is an element in the ring of integers. I can multiply that by 5. That's still going to be in the first ideal. Then I can subtract 2 times that. So this will be the second generator of this ideal. If you think about it really, this is just, 5 halves is like 1 plus root of negative 39. This is 2 of that, so their difference is like 1/2 of that. So really, this generator actually belongs to the first ideal. So instead there's a lot of time, this type of factorization will give something look a little bit different than you get from other ways, but essentially they're sort of the same thing after these surfer. Okay, so in other words, it also tells you that these generators, they're mostly not unique. Okay, so maybe I have time to do another example. Let's go back to the example of Q adjoin I and see what we have. So this is my F. My OF is just D adjoin I. Okay, I want to take alpha to be just I, and the minimum polynomial in this case is x squared minus 1. Excuse me, x squared plus 1. Of course. Okay, so for p equals 2, I want to know that this is actually, because my generator really generates all of OF, so the theorem, the factorization theorem I had earlier, so this theorem here actually works for all the prime p. So for p equals 2, what we see is the following. So I have my hx bar, which is x squared plus 1, but this is congruent to x squared plus 2x plus 1, and this is x plus 1 squared, mod 2. And what this tells me in terms of factorization is that the ideal 2 in this ring of Gaussian integers is just I plus 1 squared. Earlier on, we talked about this as 2 is actually, I actually did write this, so square times with a negative I, right? So this is a unit. Once you multiply something with a unit, it doesn't really change what the ideal is. So that when you take ideals, this unit will kind of go away. So this is somehow how it agrees with our original one, except that we're off by a unit. Of course, the original one, maybe you can get more precise with the units. For prime p of 4k plus 3, now I want to solve this mod p, but watch this. So note that negative 1 is not a square mod p. So this is in fact irreducible mod p. Okay? I'm just going to take this as a fact. You you can deduce this from the order of. You look at the order of this, because this is R. This is R. No, this is not divisible by 4. Basically, that's what's happening. The order is p minus 1. So in this case, prime p is just p comma with. I mean, you can still put it into the formula that we had earlier. So this is going to be I squared plus 1, but then you realize this is just 0. So, and of course 0 is a multiple of p, so just a p. In this case, you don't get any sort of additional factorizations. And for p of type 4k plus 1, this will give me. So in this case, when you model the 4k plus 1 type prime, there's -1 is a square root. It's a square in mod p. So you can have it like alpha x plus alpha. Or some alpha such that alpha square is -1 mod p. Okay, and in this case, you should get this. Oh, sorry. Yeah, that's fine. Let's leave it like this. Okay, but it's not. I mean, it will require some work to show that this is actually equal to some u plus I. Alpha is I. It will require some work to show this is actually a principal ideal. You can find a u plus iv such that, I guess, u squared plus v squared equals p. So therefore, for p is a multiple of this one. Oh, sorry. This is what am I writing? Sorry. I minus one. Right. That's better. Right? Oh, I should have used alpha. Maybe I used another number. Yeah, I should use another element. It's confusing. Call it beta. It's terrible. It's terrible. In the theorem, because in the theorem it was like I is R. Anyway. And of course, the relation between beta and u and v, you kind of see from here that probably you can see this from, because I beta, if you take v times I beta, you get iv plus beta v. So better beta v is congruent to u mod p, as it turns out. Maybe we can do an example, really quick example. So let's say p equals 13. Okay. So what is h bar x? Is x squared plus 1. It's the same as x squared minus 25? Right? 1 plus 25 is 26, right? This is x plus 5, x minus 5. Therefore, you have 13 equals to 13 I plus 5, 13 I plus I minus 5. Okay? So on the other hand, you know this factor is 2 plus 3i, 2 minus 3i. So which is which? So let's see. I think these two are equal. Here's why. Claim 13 I5 is equal to 2 plus 3i. Okay. So why is that? Let's maybe show this one. Let's show this one actually belongs here. So you can do 3 times I plus 5. Coming from the first one. And then you subtract 13. you get this. And so that basically shows that the inclusion this way. And you can show the inclusion the other way by hand, namely 13 is really, it's in here, and then I plus 5 is equal to, no idea. Actually I do know. Hold on a second. Something like 1 plus I. It works. Okay. Anyways, so these two shows the other inclusion. So that's so this is how this theorem compares with the factorization we have known before. Are there any questions? Maybe for the last couple of minutes, let me introduce some terms first. Oh, they're already ending. Sorry. Really quick, a couple of terms. So these things called ramification. Remember, this is a factorization the page we had earlier. So this is called ramification index or ramification degree. So in the factorization, we solve for Q joint. So these exponents. In the factorization we have over here, for all kinds of things, only this one. This is for most of them, for each factor, it's a simple factor. Only this one has multiplicity 2. So this is a case of Ramified. This is because the corresponding E is bigger than 1. So it's a general. Let me write over here. So F over Q is E. So over here is E equals. So if EI bigger than 1, this is called PI is called ramified. If sum of EI is bigger than 1, we say P is ramified. So as long as one of the exponent here is not 1, so this prime P is called ramified. Not ramified is called unramified.